Hello everyone, welcome back. Let's continue with the new topic today. So today we'll be talking about friction and hysteresis. So we have been talking about compliant mechanisms since we started this course, and we learned about various advantages. So yes, it's a monolithic design, it's elastic. Yes, we can control various degrees of freedom. We also say that there is no sliding friction, and because of that, we can get higher precision, repeatability, and because it's a monolithic design, so we can also have a miniaturization. So one of the thing we have been pointing out several times is the friction, and why is so important? Why is it has a detrimental effect if we are looking for precision? So I think we'll look at it and what are the characteristics and how it hampers, how it um, helps, or what we can say, how it deteriorates the performance. And of course, it has certain advantages in terms of damping, but otherwise, it creates a lot of problems when it comes to achieving precision or better repeatability. So we'll take a very simple example, and suppose if we have body L, so this body, and connected with an elastic element, it can be a component or it can be a spring. So with the stiffness C here, so it can be simply a bar also. So this can be connected to a body which is of interest to us, and the stiffness of the link or the spring which is through which is connected, it has a stiffness C. So what will happen? So of course now we are talking about friction, so there is a sliding friction here, and there is a friction force involved. So it can be because of the weight, or is there might be some force acting, so there will be force in the normal direction, and then you have friction force that is equal to mu n also. So most of the time we can consider a very simple model, so Coulomb friction model, and then we can just try to see what is the effect. And capital F is the actuation force or the external force what we are applying on the body, and try to see what is the displacement. So small f is the displacement, associated deflection or the displacement of the body. So if this is the scenario, what will happen? And what we realize that if we apply this force F in this direction, so if the body has to move, what what it has to always do, or what is important is this external force, unless it's greater than the friction force, the body will not move. So if that force, no matter how big or small, if it's below the friction force value, that is W in this case, which can be related to N, if it's not more than W, if the external force is not greater than W, the body is not going to move. So I think it's very easy to understand, and I think whenever we apply certain force, yeah, there will be. So if there is a N here, so mu N will be the force acting in this direction. But suppose if there is no movement, in that case, the friction force will simply readjust. So even if we have this external force and which is less than W, yeah, this force W is a readjust till it reaches that value, till F reaches uh, value W, then only it starts moving. It can, we can do vice versa. So if we move on, what we realize that very simple case again, and we just say these points or P0 or Pn we say here. So P0, P1, P2, P3, P4, P5, P6 on the diagram. So force, external force versus the displacement, the deflection, if we try to plot in this case, what we realize that when we are at this point, P naught, P0, and of course there is no force, force is 0, there is no displacement also. What happens in this case? What happens when we start applying the force? So although there is a spring attached here, but if there is no deflection, there will be no force, there will be no spring force acting. So if there is force applied and which is smaller than W, it will be simply adjusted by this W, the friction force I would say, which is equal to F, and it's self-adjusting. So this value will be less than W. So it has a self-adjusting nature. And if we talk about Coulomb force, so it's a friction force, and this is V. We talk about what we know that when it's not moving, then this is simply moving from here to here, depending on what is the intended motion. So it will self-adjust, and that is the property which makes it difficult. So what happens as we start applying the force? Force will increase till this point, and this is W. So till it reaches, there is no motion. So no motion is induced till the force F reaches the value W, and this case is 0 to 1, P0 to P1. So it will just, so we apply the force will simply increase, but there will be no associated deflection in this case, and therefore there is no spring force also, because there is no deflection there. So as we move, so we move from 0 to 1. What happens here? So at 1, now the force, now F is larger, so this is larger than whatever is the friction value here, maximum friction value. So it means now it will deflect. And if we try to make the free body diagram, this is F and this is your W. And of course, then there will be deflection F and a stiffness C. So F is nothing but W plus CF. So stiffness versus displacement. So of course, now what we see here, as we keep increasing this F, this displacement will also increase and slope will be C. So it will start moving in this direction, and this is the stiffness. The slope will be the stiffness of the spring. So the body will start moving and the spring will also start deflecting. So there will be deflection in the spring, and that will balance the external force. So P1 to P2. So as we keep moving, and suppose at 2 we want to stop, what will happen? So as we are moving in that towards right, this is what we get. So 1 to 2. So as we reach 2 and we want to reverse the motion, so we want a reversal. But what happens at 2? So the body stops at P2, so there is force applied. But what happens that at that point there is no motion, but the force is not same. Now force has to change. Why? Because yes, this is C and F2 we call it, whatever is the deflection, that is the force applied by the spring. This was the force. Initially when we are moving towards right, the friction force was along this direction. This was W, friction force. But the moment we stops and try to reverse, this will readjust. So there is no motion, there is no change in the displacement, but there will be change in F. F is no more constant, and it will start reducing, come to 0, and then as it starts moving towards left, the, the direction changes. So it will reduce to W, so 0, and then it reverses to another W. So it will reach here, and that's why we have 2W. So whatever is the friction force, twice the force, the external force will be reduced, but there is no deflection. The position is still there. So 2 to 3. So we'll reach from 2 to 3. There is no deflection, but there is drop. Force will change by this amount to W. And then only it will, so it will start moving this way. So we are here. Now the motion is reversed. Now it's moving this way. So of course then this will continue. So P3 to P4. So and it can continue further. What also happens at reaches 4, P4, F is 0. There is no external force acting now. But there is still some deflection, F4. And why? Because as it was reversing, the friction force was acting this way, and the spring force was CF4. So there was no friction, there is no external force. That F is now 0, but in a way the block got stuck there at 4. So there is no force, but we have a deflection. And what is that deflection? That is equal to, because the spring force is balanced by the friction force, and therefore that deflection F4 is W by C. So this is the value we have, F4. So that displacement, that deflection will be still there. It will not go to point O, P naught, unless we push it. So when we started from 0, then we went up, and then 2, 3, and then although force is 0, but there is still some deflection, which is F4. So that is from position 3 to position 4. As we continue further, we can keep moving and we can reach at 5 similarly. And yeah, we want to again from position 5, we want to come back. So want to reverse, and the same thing will happen at point from point 5 to 6, because there will be readjustment. So the orientation or the direction of the friction force changes, because now the motion is getting reversed. Now from left, now it tries to move towards right. So again 2W term will come into the picture. So it will increase, and when we reach 6, then only it will start moving this way. So that's what we see here. So that's how we can complete the cycle. So so what we see, that if we are reversing the motion, they are taking different path, and this is the curve of the force versus displacement curve. What we see, once it encloses an area, we say it's a hysteresis, and this is detrimental, because what happens is, suppose when there is no force acting, what is the position? And it's very difficult to say, because it can be anywhere in between the two. So from it may be at 0 if it's like coming this way and then coming from the right and then left, will be here. But if it's left to right, it will stop here. And if we just do some random movement and leave it, it will stay anywhere in between. So in a way, the position can be, so this curve, what it represents is the outer boundary is, and the position can be anywhere when we leave it. So we apply a force and we stop. So certain force we applied. This is the uncertainty we have at any point. And that's why we have this SV. So although what we see here is there is no gap, there is no clearance in this case, and but we still find that there is uncertainty. And of course, this is termed as hysteresis loop, and it's mainly because of the friction and the stiffness. What we also have to understand, whenever we are trying to get this kind of plot, we should reverse the motion few times so that we get this sort of loop consistently. What happens if, what is this dotted line? So if there is no, if W is 0, that is dotted line, that is the dotted line. So it means it's quite repeatable, right? The force versus displacement is unknown, and the C is the stiffness. So by some means, if it's a floating and there is no contact between the frame and the body. What we realize that is repeatable. There is no hysteresis kind of thing. And that's why every time we talk about precision, we also talk about friction. So this is the hysteresis, and the associated uncertainty what we have here, what we just explained. It behaves like a play, a backlash. There is some kind of clearance, but in reality, actually the body can be rigidly connected, not rigidly, but connected by a member. But there is no gap in between. There is no gap. There is no gap. But still, because of this friction and this limited stiffness of this bar, we experience that, and that's why it's called virtual backlash. And this is the positioning uncertainty we will have all the time. So whenever there is a friction involved, or if there is a sliding contact, so because of the mu, so many times this is mu n, the coefficient of friction, and the normal load. So coefficient of friction if between the surfaces, if that is involved, if there is the stiffness, so limited stiffness of the member, connecting member, if it's there, we will always have play. We will always have that backlash, and that's why it's called virtual play or virtual backlash, and that is equal to 2 times your friction value divided by the stiffness. So that is this is the amount we are talking about. And this is something which is detrimental if we want to achieve precision. So if we just look at the expression, we can minimize if we can reduce the friction by some means. So we have, if it has to be there, then it has to be managed. So the mu value, if it can be reduced, and or if the structure is stiff, or if you can increase the structural stiffness. And that's why many times we are talking about design for stiffness, designed to achieve higher stiffness. So if that is the case, then to some extent we can minimize this virtual play. And this is what it look like. If we lower the friction, this value will get reduced, and therefore associated SV, the virtual play will also get reduced. If we have higher stiffness, the slope will increase. The slope will increase, and because of that, this SB will also get reduced. So that's why we are looking for lower friction and higher stiffness. And what we also realize, this is the reason we are talking about compliant mechanisms or flexure bearings or other kinds of bearing, so that we can avoid any kind of friction force. So very simple example, one body there connected with the elastic member, with the elastic structure, and this is the kind of play we will get even though there is no physical clearance or gap between the components. So in general, so virtual backlash either in mechanisms or frames is highly undesirable, and it has a very adverse effect on accuracy. So if you are looking for precision application, if you want to achieve a repeatability of the order of micron or nanometer kind of thing, we have to seriously look into this effect, and we may have to also find a way to minimize this friction associated error, which is the virtual play or virtual backlash. What happens if we have backlash or play involved? How this hysteresis curve will change? So if we just look at this diagram and we start again, what we realize that, yeah, S1 and S2 is there, and then again same the stiffness we have, but here we will have the same drop 2 times W, and then it will come like this, and then again S1 and S2 we can check. So if we look at total play is from here to here, and what we realize that when W is not there, then this is the because of the play in the system S1 plus S2, but we have to also include this component, which is the virtual play associated, so 2 W by C. So this will be the total uncertainty. So just one member with the two gaps or clearances with some stiffness C. This is the uncertainty we are talking about. So what happens if there are many components, and it can be just C1, C2, C3 is springs, but they also represents links with the stiffness C1, C2 and C3, and this we can't call it L1 and L2. They are different bodies which have a physical contact or sliding friction with the frame. And if that is the case, two bodies and three springs, what will happen? What will be the play? And similarly, if we move, what we realize that first we feel that C1 stiffness, but as it starts moving, then we have two springs in series C1 and C2, so deflection will get added. So that's why we have the inverse. And once all the three in action, then we have this. Similarly, when we reverse, we'll have all the three in picture, and then also these are the friction forces. It will be affected in a stepwise. So initially, how the forces are changing, that will determine how how the bodies are slipping. So first is L1 and then it's L2, and that's how. So first C1 will get deflect, then L1 will start moving, then C2 will come into the picture, then W2, the L2 body 2 will start moving, then C3. So that's how slowly the entire thing will start moving, and then as we reverse, it also reverses one by one. And when we try to find the overall also uncertainty or virtual play, what we realize that is a 2 times the total virtual play here, 2 times the friction value. So W1 and W2 we have here into the effective stiffness divided by the effective stiffness. So the inverse here we see. And so as we keep adding things, what we realize that there are many, the hysteresis curve now getting smoother, and then but still we will have a hysteresis and virtual play in the picture. So what we find that is distributed throughout the structure, even if it's a lump now, but it's distributed, and there is a concept of walking slip front. So as we move towards right, the slip front will start moving slowly, starts moving towards left. So the slip front moves as the load applied and progresses to the entire structure. So this is how it will move. And so very general case we considered, and from one body to many bodies, and then we can also consider it as a continuous body continuum, take it to the continuum, and then in similar way we can also proceed. So we can talk about different problem where friction is load dependent. In the earlier case, the friction was not load dependent, it was constant. But if we consider this case, and if we try to think about it closely, what we realize that this is a very common case, because there is a guided, this body is guided, moving, but then force is applied somewhere else. So fix, and then what happens if the force is applied, which is not along the body but away from the body. And this is very common case when we do any kind of automation, because there are guideways, but there is an actuator also. The actuator can be off. And what happens in this case? So if the force is applied at a point which is with an offset b from the center axis, and the length of the block or the guide can say a, what will happen? And yes, we get this kind of hysteresis plot which is load dependent. And why is there? Because if we do the moment equilibrium, what we find that as we start applying the force, it gets tilted and these two edges will come in contact, and then the friction will be applied at the, so there will be normal force acting at the two corners, and there will be associated friction force W. And if we just try to find n, what we find then n times A equal to F times B, and therefore the normal reaction force at the 2 points will be F times B by A. So it's a function of B and A. B large, N will be also large. So we have to think about it. If A is the width, is the length of the slider is big, then again the your normal force will get reduced. So these parameters will have a different effect. So if B is large, if this is increasing, this will also increase. If this will increase, this will get reduced. So A will have A will try to reduce, but B will try to increase N. And we can always relate it to jamming of things when we try to slide things on the guides. So if we look at it and now try to balance, so if it starts moving, so as the load increases, slider may starts to move towards the right. Why I am saying may, I will come to that. But assuming that it starts moving towards the right, what is the equilibrium condition? So if we write the forces, this F is equal to the deflection, whatever is the deflection we have. So spring deflection. So on the body we'll have this CF acting, and then of course this W and this W, 2W to 2 mu n is there, and what we find n is B by A, And if we substitute, what we realize that capital F times F, which is the slope, or the stiffness, what we can say, mm, there is added parameter here, which is minus 1 minus 2 mu B by A. Mu is coefficient of friction and B by A is also there. So it starts from 0. So good thing is when force is 0, there is no deflection here. So that is good. But as we start increasing the force, we can see that it's a load dependent, that it varies. But okay, as it moves, it will move in this direction with this slope. As it reverse the direction, what will happen? This direction will change, and that's why we have minus sign here. And once we have that, we will get plus sign here. So okay, drop will be again to W, but now it reverses with a different slope, which is 1 plus C divided by 1 plus 2 mu B by A. So that's why it's called butterfly time. And here it's a function of F. It's not the friction value is a function of F. So here the friction is load dependent and the stiffness is dependent on the direction of motion, right? As it's moving towards the right, it's a steeper. As it's moving towards left, it has different value and also function of friction coefficient. So this is not constant, but it's changing. And it happens when we are applying force which is away from the guides. And again here the virtual plane is dependent on the load, and this is the value for mu B by A F by C. That's the virtual plane we will have. What happens if we apply force F but it doesn't move? So doesn't move means there is no deflection, and this F is balanced by 2W, which is 2 mu n, right? Where n is F B by A. So if this value 2 mu B by A is greater than 1, or if we rearrange, what we realize that mu is greater than A by 2B, so function of A and B. So what we can say is, if so this angle, so this we can also relate with the tan inverse mu and the angle related to friction, so tan inverse mu, and they are the function of A by 2B. So if mu is larger than this value B by A by 2B, but we realize that no matter how large is the force, it will not move. It means it will get jammed. So it means what it also says, A by 2B. So A small means again highly likely it will get jammed. B large, again highly likely it will get jammed. So, or if you want to work other way around. B has to be closer, B has to be smaller, and A has to be longer so that the jamming may not happen. So we can also relate it to the bushing design, the placement of bushing when we design the guides. And so these are all friction related issue, and I, I think one should be able to now relate why friction is not desired many times, or if it's there, how to manage it. So if it comes to managing friction, so if there is a friction involved and we cannot get away with the sliding friction, what to do? We may have to find some ways for friction alleviation. And very common example, and we do many times whenever we try to pull out cork or something which is stuck in a bottle. Usually if we just try to pull, so just pulling it, so the intended motion is just against the bottle, against that this direction. So this is the intended motion. Of course, the entire friction force will be working against, and sometimes that is too big and we may not be able to pull it out. So we can try, but it so the strategy many times is what we do is we combine the motion, we twist it and then pull it. And by twisting, what we do basically, we are also imparting this rotation motion. And what friction sees is what is the motion, what is the intended motion. So in this case, it's purely in this direction. So that's why the force was in the downward direction. But in this case, once we have this rotation involved together with this pulling, it will, so the direction will be somewhat inclined. So the force will be also, the total friction force will be against that. And what we have to only apply along the axial direction is the component in the vertical direction, the component. And that's why as we start twisting, the because of this arrangement, because the Vt and Vl, this relationship, we'll get the direction of V. So the Fw direction changes, and then the ultimately the force which is required to pull the cork or the material out of that stuck bottle or any kind of pipe is only this much. So that works. So what we have to remember is friction is always in the opposite direction to the slipping velocity. What is the slip direction? How is going to slip? Whether it's just slipping in the axial direction or whether it's getting twisted. So it has a combined motion. So rotation of the cork alleviates the friction. So this can be very good strategy. So though we apply it very often, but whether we can apply when designing machines or designing things where friction is involved, and we cannot get away with that. So very nice design, good designs, and that was implemented. So what we see here is a scale design, physical scale, and then we want to have a very high accuracy. What limits is the friction here. So pivot, and so there will be always some friction here or here depending on which way. So some mass is added here and try to measure. It always get limited by what is the accuracy here, because there will be always some friction there, and it will add to that value. So that is the uncertainty we'll have. So it can get locked anywhere, just like the previous case where we have the body and the spring attached, and It's a zero, but it's not zero because it can always get stuck at certain location if it's within that SV, that the virtual play. Similarly, here also it can get stuck, and that amounts to the error in the measurement. So if you want to minimize that error, we can always use that combining motion. So here that's what has been done. So very nice design is so from Professor Sumer's book. And again, what you see here that this the scale, this scale is now supported on these two V rollers, and they are rotating in opposite direction. So it's rotating like this. So you see here as well. So side view. So this is front view, and so this is rotating in a way, and there is another one at the back which is rotating in the opposite direction. And if we check this figure, what we realize, because of this rotation, hmm, these rotating V rollers towards one another, and they support the shaft, this shaft, and edges actually, because what happens if it tries to move towards one side, the equivalent weight on that side will increase, so the effective friction will also increase, so it will try to push it back. Similarly, if it moves towards this side, the weight on this side will increase, and so it will bring it to equilibrium on its own. So very good design. What it also does, because it's rotating in this way, the friction force thing in this direction, one component, mind one component, but at the same time, if it's a swinging, that component is also there. But primarily, the most of the component, because these V rollers are now rotating, the friction force is in this direction, plus or minus direction. It has very little component on this direction. It means effectively the friction uh, which restrict this motion because of the uneven weights or the masses is very small, and it means we can increase the accuracy of this scale by combining this motion. So very clever design, and it has been used. So it reduces the friction associated with the scale rotation. So just by implementing that rotating V rollers and by combining that motion, actually we change the direction of the friction force, and effective friction in this direction, which limits the accuracy of the scale, actually minimizes, and it increases the accuracy of these scales. So you don't need a very sophisticated system, but a simple mechanical ingenuity, I would say. And the concept what we learn, we can apply and can use it to design these precision devices. So one can always try build these things and try on your own up to what extent you can do. So very good example of again the combined motion, and this was out of my PhD work, and here I talked about flexible instrument, and when we move inside a curved endoscope, how we can improve the motion and force transmission of these instrument. And we use the same concept, we combined it, and we try to see what is the effect if we combine, and whether we can improve the motion force transmissibility of the instruments when we are trying to use for medical application. And for many medical application where in those interventions, if we have to steer needles and or some kind of endoscopes or catheters, this can always improve the fidelity, the motion fidelity or force fidelity at the end, because we are always working at the base, but the tip is far away from the uh, from from our hand or from where we are operating. So this concept can be also used to design. So here the precision is of different nature. It's not about like reaching the micron line kind of accuracies, but it's more towards fidelity, the motion and force fidelity. And we'll talk about this thing in detail in the next lecture. So I'll stop here today. Thank you.